Kasi ay nahan hypet kanoda hypet kanota ukibaniya to masi amu repeat to ke masi date kya no
1 sir, July 1.
1/7/2021 ka. Sida aina logado hi se mass spectrograph hai ko. Mass spectrograph sida akoina makhan ani lei ko. Banbridge mass spectrograph hai bama. Adai amana stone mass spectrograph. So we have two types of mass spectrograph. Sinataba topa mass spectrograph lay atubu noigi syllabus ta yauriji ani jini atagi noigi kanogi semester ki fourth semester ki examination da su adum working principle and theory of Banbridge mass spectrograph, the stone mass spectrograph and adum alternate years ta adum hangi. Aduna se adum question du su ay adum tharake si ani ji manung da ama adum soidan adum hangi. Sida sigi theory naina ba sida ay kano su video su ay yinguna si han bata my basic kara takao ba kara aina su mamangi class ta I pet takrabani mamangi means mamangi semester kita sida apana se force acting on a charge Q placed in a uniform electric field. The force force equal to QE, where Q is the charge, E is the electric field. Other tadi, when electric field command established tawni hai tadi, when plate ani low re, then now plate ani si positive, negative terminal of a battery samjalle. Other tadi between the two plates, there is a uniform electric field E. So the force, magnitude of the force is QE. I think charge particle ama uniform electric field the move to kera as well as rest like kera. Momo the exact of force to force is given by QE, where Q is the charge, E is the electric field. Kaya ko lower ba? Silo chi the pasana silo ai class ti ano physical class to boga chamana na I arrange to do ni ko. Sumna ge noi mobile yeng bo noi yeng ba yaroi table da pamu adu ga check kolom par ga selu khang da ba su khang di na dum hai ro. Yare ko physical class ka chamana na ai arrange to do ni. Boy kolom pa how drabo.
Aisha.
Irabo lorabo.
Loide.
Loide. Loro. Lore haro. V equal to QE divided by M into T. So this is the velocity of the charged particle after time T. So given the charge is initially at rest. If the charge is initially at rest, then U will be 0. So velocity of this charge after time t is qt divided by m.
Lỗi sir.
Then aduna sigi mass spectrograph sita I cannot the diagram okay. So sigi si na syllabus niko si center se are city chale to anode sida kano si charge produced already, then it passes through 2 electrodes. Sida anode che si anode and thai si ubra anode sida ki charge produced already, then si magi ionization chamber sida mulai aduga sida bana sida S1 and thai si ubra S1 che S1 is slit amni small slit amni sida nasagi charge enter tore, then sida kano sida velocity selector hai che sida kano si positive ion beam ji lae aduga S3 nama thai sida ubra sigi S3 sisu slit amne bako makhun amni hole amani hariba hole sida nasagi electric field ji sigi bar black bar ani je we call velocity selector. Sejita kano je electric field je apply torni, since electric field apply torni na say charge parabolic param the move torni adubu som the karama sakarni adubu masigi holes the pass torakpa kano se charge particle khadi yaw ne abo yaw rani adugi charge particle je amuka dore magnetic field sigi dot lady say it indicates a magnetic field sida dot namisi uidana sigi dot sina it indicates a perpendicular magnetic field sigi magnetic field ji apply tornina charge will move in a circular orbit adu ai ngasai hayo gre ngasai force due to magnetic field Fm equal to QVB and hydro. Because of that magnetic field, the charge will move in a circular orbit. Hydro. Yareko. Adu si I sigi write up so I noida tharake. Adu ba sigi di an ba hobunina. No si di diagram si I Tharake adu uji si makada kano to getu yeng se Sida nasagi ionization region hai je mana region 1, 2, 3, 4 and kaido idana. Ada 1 jidana na ionization to we have. Ionization to ba ji kai no haita di kona atom consists of positively charged particles we call protons, the neutrons yaure. Atom the yaw si electron proton neutrons in the nucleus and electrons are revolving around the nucleus. Other chumnaki charge an atom is electrically neutral. Adu huzik apana mass spectrograph sida sinana bagi damaktar ketawi. We need ionization, ion form the positive ion form the Thambadaka way, that is called ionization. Ionized or in the form of ions, positive ion when later. Electron we do not consider because electron city very lightweight ni lightweight oibanina electron ki kanoti akoi khanate akoina pamisi positively charged particles to name either proton or helium nucleus. Sina singpatu. Haiba ion form the lava say sigi accelerating voltage sama apply tore. Si atai kasunate force equal to QE to E to saukhatna by the we have to apply more voltage. Adu malay re. Adagi sige third si the velocity selector right? Si the plus and amathata ire makata minus ire. Si atai kasunate plus ay the battery amagi positive terminal do samjali hai then makagi minus ibusina battery amagi negative terminal do sammi hai so that the charge moves in this electric field ado sida arrow ma lai sigi sida charge phaudorakatoni atopa charge singdi sigi hole sigi kanosna block tawani only sigi holes in the lakwa charge to full ane S3 and mamangi figure the yaugib do adu then sida sigi dot indicates a uniform magnetic field adu sigi magnetic field sida lae sigi magnetic field sida kan sida na sigi charge will move in a circular path depending on the ratio of mass to charge ratio. Sida strike tawre, sida strike tawre, sida strike tawre. So this is detector. Detector is kamai thamge the photographic plate amathami photographic plate to the charge me strike tawgi magi image. Adu taraga lehogani adu yenga kanda ai kayam magi radius to Marona radius on doing it, Siki radius on doing him. I pet pop that about. Sida B out of page, I say. The pen of the paper, the perpendicular outward when a tolay hiding. Aduga sums into Haramagana. Instead of this dot, if there is into sign, into lambda, the cross sign lambda, the magnetic field is acting perpendicular into the plane of the paper. And this dot indicates that the magnetic field is acting perpendicular outward. Anyway.
And then a region where the isotopes are separated. So that would be region 4. So essentially what happens is you've got a bunch of atoms. They're all the same element. They go through an ionization process, so they've all got the same charge, but of course we've got some different isotopes in there, and that means we've got some different masses. Now these charges are put through some accelerating plates. That's going to give them some kinetic energy, some speed, and they're going to have a fairly wide range of speeds. However, when they come into this velocity selector region or speed selector region, which consists of crossed electric and magnetic fields, what happens is that if the particles are either going too fast or too slow, they'll miss the opening on the other side. So they have to be going at exactly the right speed to make it through into this 4th region. So in this region here, we're just nailing down that speed, so it's essentially at a constant value. And then in the last region, the magnetic fields will separate the different isotopes. Let's take a look at that second region in which the ions are being accelerated across some plates with some voltage across them. So they're going to enter some hole on this plate and then they'll exit a hole on the other plate. Now, assuming that the ions come into that first plate with zero velocity, which won't necessarily be the case, but assuming it is, we can work out how much speed those ions are going to gain as they cross the plates. So their increase in kinetic energy, assuming they start from rest, would be a half mv squared. And that's coming from a loss in electric potential energy, which would be given by the charge on the ions times the voltage that they're accelerated through. If we do a little bit of rearranging, we can solve for the speed at the far side of the plates, and that'll be given by 2q delta v divided by m. So the speed over on this side is going to be v if they started from zero speed. So the speed that we just calculated, that assumes the ions entered with zero speed. Not necessarily the truth. There will be a small range of speeds coming out this side of the plate. Let's take a look at the third region of the mass spectrometer, which is called the Speed Selector. So we've got the positive ions coming in, and they've got a narrow range of speeds. They enter the hole here, and there's parallel plates creating a vertical electric field. So let's say that we've got a positive plate up here, positive voltage connected to that plate, and a negative plate down here. Then of course these positive charges are going to experience a downwards electric force. Now if we were to also have a magnetic force and we made that magnetic force upwards, then potentially those two forces could cancel out. But what's really neat is the magnetic force, it depends on speed. The magnetic force is given by QVB. So what we can basically do is select our speed so that it works like this. If our speed is too great, then the magnetic force is going to be bigger, and what's going to happen is the particles are going to be deflected upwards if they're going too fast. And if they're going too slow, of course they're going to be deflected downwards because the electric field's going to be bigger. And it's only if the two forces are exactly equal that they're going to make it through this hole here and enter the next region, region 4 of the mass spectrometer. Now if we want these two forces to be equal, then that QVB, the magnetic force, would have to equal Q times E, the electric force. So we can say that QVB equals QE if we've got just the right speed. Q's of course cancel out. So what we get is that the speed must be equal to the electric field divided by the magnetic field. And so the way we select the speed that we want is we typically keep that magnetic field fixed and we vary the electric field so that we get exactly the speed that we want. So we're going to select the speed that we want to go through. Now, of course, in terms of what direction will our magnetic field be in, we're going to use the hand rule, of course. The particles are moving to the right, so if we point our fingers to the right in the direction that they're moving, and we want our palm to go in the direction of the magnetic field, such that we're going to get a force in the direction our thumb points, which is upwards. Now, if you use your right hand, that will mean we've got a magnetic field that goes into the board. So we'd like a magnetic field that goes into the board inside the velocity selector region. And what that now means is that we're going to know how fast these particles are going when they enter that fourth region of the mass spectrometer. Now, these ions that all now have the same speed enter a uniform magnetic field region, which of course causes a uniform circular motion for those ions. And we know the only force that's acting is that magnetic force QVB, and that has to equal the net force for uniform circular motion, which is that mv squared over r. We can then write that the radius must be equal to mv squared divided by QVB. And we can cancel out a v, and we get the expression that r must be equal to the mass times v over qb. I separated v and qb because we know those are all constants, so that the radius will simply be proportional to the mass, and these numbers here, these constants here, will all be known. And that means that we're going to be able to calculate, by measuring the radius, we're going to be able to calculate the mass of those ions. So this mass spectrometer serves a very useful purpose. Not only does it measure the mass of the different isotopes, but it also allows us to separate those isotopes, and it means we're going to be able to make samples that are purely of one type of isotope using the idea of a mass spectrometer. Okay, I have a few IB questions for you here. Read over the question, try it out, and then come back for the answer. So hopefully in this question you said that you can measure the mass of ions using a mass spectrometer. So the key idea in this question is that these other options, an isotope, a molecule, an atom, they don't necessarily have charge. So we have to have charge to measure mass in a mass spectrometer. Okay, a second question. Pause the video, try it out, and then come back for the answer. And hopefully you said A, and the reason for that is that you've got an electric field that's pointing this way in the speed selector region. That means you have to have a magnetic force that's pushing the other way. And so if we're using, we've got positive ions, and that means we can use our right hand. Your hand should do this type of thing so that we'd have a force going in this direction. You've got the particles moving in this direction, and your palm should be facing outwards if you do that. And that means that B1 has to be out of the page. Now, as it comes in here, we're still pushing the same way. And so we'd use the same hand rule in the same way. And the magnetic field, once again, has to be out of the page. And that's all for today, folks. Thank you very much.